Welcome back, everyone. In this video, we're going to continue learning about valence bond theory, and we're going to use Lewis structures and the valence shell electron pair repulsion model to determine what we call the hybridization of atoms, and that's going to be within a molecule. So in our last video, we encountered a dilemma. We were trying to explain how methane has a tetrahedral electron domain geometry using its unpaired electrons to form covalent bonds with the hydrogen atoms. However, what we saw is that in that case, we're only going to form two bonds because we have two unpaired electrons, and it's the unpaired electrons that are forming the bonds, and that because we're using p orbitals, that they're going to be 90 degrees from each other. So we would expect bond angles of 90 degrees. We would expect to have a lone pair of electrons and only have two bonds. And so this is insufficient to explain the molecular geometry that we observe for methane. Let's propose a process, a different process that would help us to explain the observed phenomenon of methane having an electron domain geometry that's tetrahedral. So let's take those electrons that were in the ground state of carbon. So this is carbon ground state. And let's promote one of the electrons from the 2s orbital into the 2p orbital. So this would require an input of energy to make this happen. If we've done that, or once we do this, and we now have 4 unpaired electrons, therefore we could form 4 bonds. However, we still have a dilemma, and that is that we would end up with 3 bonds that are each 90 degrees from each other in 3 dimensions, and then a 4th bond that would be kind of short and stubby. So instead of using these orbitals as is, what we conceptualize is combining those atomic orbitals in order to produce a set of hybrid orbitals that are identical to each other and that are kind of a weighted average of each of the original atomic orbitals. We call this process hybridization. So if we take the 2s orbital and the 3 2p orbitals and we combine them up and make 4 identical orbitals, we see that they were 1 part s and 3 parts p. That comes from the fact that we had 3 p orbitals and 1 s orbital. Therefore, we would call that hybridization sp3. That designates how many parts s and how many parts p those 4 orbitals are. And notice that the energy of those sp3 orbitals is going to be in between the energy of the 2s and the 2p orbitals. And it's actually closer to the 2p orbitals because there's more of them. So the sp3 orbitals, both in terms of their naming and in terms of their energy, are more similar to the p orbitals that made them up than the s orbital that made them up. And so we used 4 atomic orbitals, a 2s and 3 different 2p orbitals, and we combined them together and made 4 identical hybrid orbitals that have the designation sp3. This is just another way of looking at that process that we just described. We took a 2s orbital with the 2p orbitals, and we kind of think of it as you can deconstruct them and then put them back together so that way they are equal parts s and p. When that occurs, what we see is that the resulting orbitals end up taking the shape of the tetrahedron that we saw tetrahedral molecules like methane take. We're not going to go into the reason for that, but essentially it has to do with the mathematics of combining the wave functions, of adding together those different wave functions. And notice also that for sake of simplicity, that in the overall diagram, we have not shown the orange lobes, although they are still there. As I mentioned earlier, the notation sp3 indicates that it is a quarter part S and 3/4 parts P. Understanding that this is the reason for the notation is important because later we're going to use other notations based on which atomic orbitals were combined. And the orbitals that are created, the hybrid orbitals, are centered around the atom from which they originate. So we have taken these 4 different orbitals that were centered around the nucleus of the carbon atom, created 4 hybrids that are also still centered around the nucleus. And now we're able to form 4 bonds. And because we're using 4 identical orbitals, they will be of equal length and strength. So let's draw an analogy here. Let's say that you wanted to make a smoothie and you have the smoothie, you want it to be 1 part strawberry, 3 parts peaches. What you would do is you'd take those, you'd cut up and prepare the fruit, put them into the blender, blend it all up, and then pour out 4 identical smoothies. And that's because you've mixed together the properties of the individual fruit. And say you and 3 other friends are getting together, so you pour out 4 total smoothies. So similarly, when we think about the concept of hybridization, we take the orbitals that we started with. We imagine that we promote any electrons that are paired up to higher energy orbitals that are empty, that we combine those atomic orbitals, and that the result is the same number of orbitals, but which are identical to each other. In this case, when we have 1s and 3p orbitals, that produces 4 orbitals that are each sp3. After we've made those orbitals, then we can form bonds. So the sp3 hybrid orbitals on the carbon can then overlap with 4 individual 1s orbitals on the hydrogen atom. As it does that, because they are 109.5 degrees from each other, we can now see how we would get the tetrahedral arrangement of methane. These sp3 hybridized orbitals are found on other molecules that also have 4 electron domains. So this process of hybridization, we can extrapolate and extend to any molecule by evaluating the number of electron domains that it has. Ammonia has 4 electron domains, 3 bonding and 1 non-bonding. Because it has 4 domains, it needs 4 hybrid orbitals. Water also has 4 electron domains, 2 of them are bonding, 2 of them are non-bonding. In order to have 4 domains, which are each approximately 109.5 degrees from each other, we need to make 4 identical hybrid orbitals. So we can extend this idea to cases where we have 3 domains or 2 domains. So if you have a molecule that has 3 electron domains, instead of using 4 orbitals, we only need to use 3. Therefore, we'll use the lowest energy orbitals, which would be the 2s orbitals and then 2 individual 2p orbitals. So we can imagine a similar process, an excitation of lower energy electrons up to the higher orbital, a mixing of those orbitals to form hybrids that are equal to each other. And note that in this case, we only mixed 3 orbitals, so we have 1 orbital that is left over. That unhybridized orbital, that leftover atomic p orbital, is going to be perpendicular to the axis of the sp2 orbitals. So here we would have our trigonal planar molecule and then a leftover p orbital. We'll talk more about what happens to that p orbital in future videos. So again, because we needed 3 identical orbitals, we took 3 orbitals to start with. One of them was an s orbital, 2 of them were p orbitals, and we combine them together to get 3 identical orbitals that are 1 part s and 2 parts p. Similarly, we can mix together a single s orbital with a single p orbital to produce a hybrid. This would be the case if we have a molecule that has 2 electron domains. So similarly, we would take and excite the ground state electrons up to the higher level in order to have them both be unpaired. We then take and combine those 2 orbitals with the electrons to form the hybrids. And then we have leftovers in the form of unhybridized p orbitals. This is what happens when we need 2 identical orbitals. And the leftover atomic orbitals, which are unhybridized, are going to be perpendicular to each other and to the axis of the sp orbitals. So again, as we saw already, the number of atomic orbitals, or the number of total orbitals, is conserved. We needed 2 hybrids, so we started mixing 2 atomic orbitals. We had 4 total orbitals to begin with, and then we have 4 to end. 2 of them are hybrids and 2 are unhybridized orbitals. So we can use the electron domain geometries in order to predict the hybridization. And this is simply because the electron domain geometry is determined based on the steric number. The steric number tells us how many total electron domains we need, and therefore that is how many hybrid orbitals that we're going to need. So you can determine the hybridization simply by looking at the molecule and determining how many electron domains the given atom has for which hybridization you're trying to determine. Let's practice here. Let's say that you have 4 different molecules. We want to know which molecules have sp2 hybrid orbitals on the carbon atom. So we've talked about this already. I'd like you to pause the video and try on your own to determine which of those carbon atoms will have sp2 hybridization. Welcome back. So how do we determine this? Well, as we mentioned already, in order to determine the hybridization, you need to know the number of electron domains. So we need to take and draw these molecules. The first molecule, CH2O, looks like what we have here on the screen. And this carbon has a total of 3 electron domains. Remember that double bonds still only count as 1 domain. We have 3 domains, so this needs 3 hybrid orbitals. So we take 3 atomic orbitals. We take 1 s and 2 p orbitals. We mix them up to get 3 orbitals that are 1 parts s and 2 parts p. For C2H6, this is that molecule. Notice that each carbon atom is actually identical because they each have 4 domains. 4 electron domains means that we need 4 hybrid orbitals. Therefore, we're going to take 1 s and all 3 p orbitals, and we're going to combine them to get 4 orbitals that are each 1 parts s and 3 parts p. So that hybridization is sp3. C2H4 looks like this. We also have 1, 2, 3 electron domains. Because we have 3 electron domains, our hybridization is sp2. Finally, C2H2 looks like this. Each carbon, notice, has 2 electron domains. Remember, triple bonds count as a single electron domain. Therefore, if we have 2 electron domains, that means that we need to have 2 hybrid orbitals that are identical. So we take 1 s and 1 p, we combine them up to get 2 orbitals that are sp hybridized. Now again, the orbitals that we choose are always going to be the lowest energy orbitals. So you always pick the s orbital and then the requisite number of p orbitals. So that way your total number of atomic orbitals you're combining is equal to the total number of hybrid orbitals you want. And the number of hybrid orbitals is equal to the steric number. All right, let's try one more. Pause the video and try this one on your own, and then I'll walk you through a solution. Welcome back. So we want to know which of these atoms in the guanidinium ion have sp2 hybrid orbitals. So this, in a way, is a little bit of a trick. And the reason is because there are some things that are missing. First of all, you need to be able to recognize that while this hydrogen or nitrogen here has 4 bonds, therefore it has a complete octet. These nitrogens do not, and so they would have lone pairs of electrons. Now, I drew the double bond between the carbon and the nitrogen up on top, but you should be able to recognize that I could have equally drawn the molecule such that the nitrogen on the left has the double bond and the other 2 nitrogens have single bonds. Therefore, this molecule has resonance. And in fact, it has a 3rd resonance structure. Let's draw that over, where the double bond would be depicted between the carbon and the nitrogen on the right. Since we have resonance here, what we see is that the hybridization of all of the atoms that are indicated here, all 3 nitrogens and the carbon, is in fact sp2 hybridized. We'll talk more about that in future videos, but you should be able to tell that A, there is resonance, and that the complete structure, the most accurate structure, is going to be a combination of all 3 resonance forms. Therefore, our bond order between the carbon nitrogen is going to be, can you figure it out? Pause and try. 1.33, 1 1/3. Okay, that's found by taking the bond order between the same carbon and nitrogen in all 3 resonance forms, summing those together and dividing by the number of resonance forms. Okay, they all have equal bond lengths, bond strengths, and you can see that when we look at the resonance form, that they all have 3 electron domains. Because they have 3 electron domains, they must be sp2 hybridized. We'll go into more detail about that in a future video, but I wanted to introduce you to this idea before we get too far ahead of ourselves. Thanks for watching. Have a wonderful day.